So once again, hello everyone. So I think we can start now. So now we'll be starting with this time domain analysis and its response. Uh, by time domain analysis, we mean to say that how the response of the system would going to behave with respect to some input and also through its natural response. So you know from your earlier classes that if I want to define an overall response, let's call it the yt of t, which is the total response, then it is basically a summation of yn of t, which is the natural response, plus yf of t, which is the forced response. So this is the forced response, this is the natural response, and this is the total response. Okay, now we also know that for computing the total response, there is a very strong relationship of the overall response with the poles and zeros of the system. Poles and zeros of the system in the frequency domain, right? So there is a very strong relationship between the time domain and the frequency domains, and we want to do some qualitative analysis of the time domain response based on the poles and zeros. So for a given transfer function, let's say we have the y of s over some input u of s is equal to let's say s plus 2 upon s plus 5. Okay, this is our transfer function where y is the output and u is the uh, input. Okay, here the 0 of the system is located at -2 and the pole of the system is located at -5. So there is only one pole and one 0, and we call it the first order system because of the first order polynomial in the denominator. Now let's say I want to compute let's put it into the block diagram, s plus 2 over s plus 5 to some input u of s and taking some output y of s. Okay, now we want to see the response y in the time domain for uh, u of t as a step signal, and we whatever the response I would going to obtain y of t, we call it the step response. Okay, now for the given step signal, we know that u of s is basically 1 by s, so we would have the y of s as s plus 2 over s plus 5. Okay, which I can write as a, if I want to compute the time response of the, or by taking the Laplace inverse, first of all we do the partial fraction and then we directly take the inverse Laplace transform to finally write the expression in the time domain. So doing the partial fraction of this expression, I would get 2 by 5 of s plus 3 by 5 over s plus 5. Okay, this you can obtain by using the partial fraction, and finally y of t I would obtain is 2 by 5 plus 3 by 5 e to the power minus 5t. Okay, now this is the overall response, and this particular response we call the forced response, and this whole part is called the natural response. Okay, this is according to our definition or to the expression what we have introduced earlier, that the total response is basically the summation of the natural response and the forced response. Okay, so these are the two responses which we are basically interested in, and in this response or domain analysis we would target some typical order systems, say first order system and second order system, while the higher order system we can approximate by the first order and second order system, and by doing the response analysis we would also define some uh, key performance indices, or what we call the specifications, to quantify the dynamics of the first order and second order response. Okay, so going to the lecture notes. So this is the expression we would have. We also call it the transient response YT and the steady state response. This steady state response is the steady state response and the transient response. And we know for the transient response that as t tends to infinity, yt of t is basically equal to 0, and what we would remain at steady state is y of ss. So this is the property associated with the transient response. Now, all real and stable systems exhibit transient phenomena to some extent before the steady state is reached. Because if the system is unstable, then there won't be any steady state response. The reason is that the response of the system would reach to infinity. So, for unstable system, there is no point to do the transient response analysis and the steady state response analysis. Now, particularly this steady state response of the system is particularly important since it indicates where the system output ends up at when time becomes large. We want to we while analyzing the closed loop system or the control system, we want to analyze that what could be the maximum or the maximum value the system could achieve in a long run. Okay, so this is a typical response what you are seeing here, which is a unit step response of some second order system. So there are some key performance indices. First of all, we'll see that what are the different criteria by which we can quantify the dynamics, and then we'll see in detail that how to compute them for a given transfer function. Okay, so this is the unit step input, which is in a straight line, which you are seeing here is a straight line. So I have drawn the input and output curve on the. So let's draw it. This is the input line, the input signal to the system, and this is some output. Okay, so see here. So around, we see that the response of the system is being settled to the input, and we define some band which is at 5%, 5% plus 5, and 5% minus 5% of this unit magnitude. So this would be our band within which our system or the response of the system is settled down, and the maximum value the output signal attains to this input signal magnitude, we call it the maximum overshoot. Okay, so this maximum overshoot is above the the unit magnitude line. Okay, and we define the rise time of the response when the response goes from zero point 0.1 to zero point 0.9 value. The time it takes to reach from zero point 0.1 value to zero point 0.9 value, we call it the rise time. The delay time, the time the response takes to reach from 0 to zero point 0.5 value, and we call it the delay time. The maximum overshoot attained at some particular time we define as this T maximum, that at this particular time the maximum overshoot is achieved. Okay, so these are some specifications to identify from the response of the system. Okay, so let's see that the maximum overshoot, or we call it the MO, YT is the unit step response. Ymax we define as the maximum value of the signal y of t, and we know it would achieve at t max. At t is equal to t max, we achieve this value y max, and yss is the steady state value of y of t. So y of t is basically would be 1 in this case, because we are seeing particularly for this response that the output is being settled down to value 1. It might be a different value, but we'll see in what cases we have those different values. So this is the fact that the maximum value of the signal would always be either greater than or equal to y of ss. This particularly equal to sign we will see in the first order system analysis, that why it comes the equal to sign, while for higher order system most of the time we would have that y max is greater than y of ss. Okay, then we define the maximum overshoot as the difference between the maximum value of the response minus and the steady state value of the response. And for computing the percentage of maximum overshoot is this y max minus yss divided by yss times 100. So this is just a percentage of the maximum overshoot. Okay, one particular significance of this maximum overshoot that we would going to use it to measure the relative stability of a control system. Why we are calling this as well or always as a control system? Because consider a plant. Okay, we have the input to the plant and we have the output from the plant. Let's call it the plant. Okay, but once we design the controller, this output of the controller, which is basically the input to the plant, is no longer free. It is uniquely described by this controller. The only free signal is some reference signal r of t. So we want to see that if we connect the controller to the plant, how it would going to behave, where this r of t is the reference signal, which is a free signal, and the response which is unique to this reference signal. So that's why we define this model as a control system, because you could do the analysis of the open loop plant and also you could do the analysis of the control system, or let's say the control system. So a system with large overshoot is usually undesirable, and the reason for this is let's see. So why do we call that the let's write this: large maximum overshoot is undesirable. The reason behind this is, let's say we recall the closed loop system. We have with the denoted signal reference input and output. Okay, now in the earlier classes we had seen several transfer functions. We had seen the y of t, that how r of t would affect y of t, how r of t would affect the signal u of t, because now u is now governed again by the closed loop system. So if I write the transfer function, let's call it the t of y of s, it is for this particular system is pc upon 1 plus pc, and if I call the transfer function of u with respect to r, we would have c over 1 plus pc. So this denominator part remains the same. Okay, now for the overshoot, we say that the large overshoot is undesirable primarily because of the signal U. The reason behind is, now here we haven't placed any actuator, and in the last class we discussed about some typical nonlinearities, and one of the nonlinearities is the saturation type. Okay, which here is the input and output. Now if I connect the actuator before the plant and see that how maximum overshoot is coming into the picture now. So U of C and U of P, this is actuator, plant and the controller. So UC is the output of the controller and UP is the input to the plant or the output of the actuator. Okay, now here this UC, if UC is containing any or higher overshoots, then it might be possible that, if and considering that the actuator is of saturation type, then it could be possible that our input could lie in this region, and the input if lie in this region, then your output would become saturated. So we do not want our output to get saturated at any point. This is the reason that we avoid to have the larger overshoots. Okay, so this is the physical significance of avoiding the large overshoots. The delay time, as we said, defined as the time required for the step response to reach 50% of its final value. Okay. Now rise time we defined as the time required for the step response to rise from 10 to 90% of its final value. And these responses are generic, I mean these specifications are generic specifications you could use with any other system. Yes, anyone has anything to say?
So in the video that you have provided, the rise time is like defined differently for a overdamped and underdamped response. For underdamped, they have defined as rise time as going from 0 to 100% in the first instant.
So we, yes, we will come on to those aspects as well, because rise time and the settling time are there are no specific definitions for those things. Okay, so some in some textbook you would see from 0 to 100%, or in some books you would see some other percentage, right? Now for the underdamped and the overdamped responses, we will see that how these generic definitions could fit into or for those specific responses. Okay. Okay, so the settling time is defined as the time required for the step response to decrease and stay within a specific percentage of its final value. So most of the time we take this plus minus 5% around the steady state value of the input, and in some textbook it is goes beyond this 5% also. So some take plus minus 5% or plus minus 7%, plus minus 10%. Okay, we will come on to those aspects also. And the steady state error is defined as the discrepancy between the output and the reference input when the steady state is reached. Okay, so the steady state error, if I describe, is the steady state error is when the steady state of the output is reached minus the steady state of the reference signal. Okay, so let's start our discussion with the first order system, that which specifications we could use to quantify the performance of the first order system. So first of all, note here that here I have defined the closed loop system, because I am using this R of S and the C of S, where R is my reference signal and C is my uh, the output of the system. And the overall closed loop system you can define by some first order system which is given here as A upon S plus A. Okay, so all this analysis, like I said, is why you can use it for the open loop analysis and the closed loop analysis. Now for unit step input, we have R of S is equal to 1 by S. Hmm? Now again writing the expression of the output, only we would have A upon S plus A, and again taking the Laplace inverse, I would obtain this C of t as 1 minus e to the power minus at, right, where this one is the forced response and this one is the natural response, and this natural response is because of the pole located at minus a in the transfer function. So this parameter a plays a significant role in determining the transient response. So this a, so when t becomes equal to 1 upon a, so if I write this t as equal to 1 upon a in this expression, I would get e to the power minus at at 0.37. Okay, in that case my c of t will become 0.63. Okay, so based on this we define the time constant, that this is the time it takes for the step response to rise to 63% of its final value, and in this case 1 upon a, it's 1 upon a. So 1 upon a becomes the time constant for the first order system. Okay, the other index is the rise time, and this we can find out by solving the above equation of the response, basically this one, hmm, for two different values by putting c of t is equal to 0.9 and putting c of t is equal to 0.1, and for this we can compute two different times, right, because we have defined the rise time as the time required to reach from 10% to 90% of its final value. Okay, and the final value of this c of t, I think it is straightforward to see that the final value would be 1, because this part would go to 0 as t tends to infinity and the remaining part would be 1. That's why we have put 0.9 and 0.1. Otherwise you have to put the 10% and the 90% of the final value. So computing the rise time, we see there is a relationship between the rise time and again the pole of the system, which is tr is equal to 2.2 by a. Okay, so having the knowledge of the pole of the closed loop system, you can determine the time constant, you can determine the rise time, and you would also can also determine the settling time. So like I said earlier that some people take 2% or 5%. Okay, so considering 2%, we have the settling time is equal to 4 by a, again expressed in terms of the pole of the system, where your c of t is 0.98. Okay, considering the 2% of the steady state time. Right? Now the most important point here is to see that the step response will never have any overshoot for any parameters. Okay, so in the first order system we do not experience the overshoot, so these are the primarily three performance indices associated with the first order systems. Okay, so do you have any doubts or question up to this point? Okay, I think it's, then we can go ahead, and I would suggest that for the second order system we will take it in the next class. We'll keep it a bit shorter so that most of the concepts are clear thoroughly. I can take some questions now to discuss either of the tutorial problems or any part of the videos that I have uploaded onto the Moodle or of the lecture notes. You can write your question in the chat box also if you want, and because I could understand that your connection might be weak or likewise others. If you do not have any queries or any doubts regarding these concepts or the tutorial problems, maybe you haven't yet solved them, try to solve them, and possibly tomorrow we can take them. Hmm. So if we don't have, then maybe we could disconnect, because I prefer to start the second order systems tomorrow. Okay. Okay, thank you.